systems can feel in that way. Okay, even though I'm not giving a full background on philosophy of mind, I want to define one term that we are going to use a lot, and that's qualia, or the singular form quale. So qualia are the individual instances of subjective consciousness, of subjective conscious experience. They're what it feels like to have certain mental states. So they are what it feels like to be you experiencing something. Roughly, you can think of qualia as essentially meaning experiences, you can translate it that way, or quale as experience. And examples of qualia include the redness of red. It's not just understanding what red is, but what it feels like to be you experiencing, seeing the redness of red. The taste of chocolate, pain from a stubbed toe, the smell of fresh cut grass, these are all qualia. Okay, so going back, we have our first assumption. We're ready for our second assumption. This raises a range of philosophical and ethical questions. If AI systems can feel, do we need to worry about how they feel? Should we trade off the feelings of AI systems and the well-being of people in any way, or not at all? And these are really challenging ethical questions. Are AI systems moral patients? We're not going to address that today. We're just going to assume the answer again. We're going to assume that there is some need for enhancing the quality of AI agent qualia. That is, there is some reason that we want to make our AI systems feel better. We want to make them happier. When we're solving this problem, we care about performance, but we also care about how the agent feels in solving the problem. Okay, these two assumptions are all that we need to define what I'm calling qualia optimization. It's a subfield of AI concerned with optimizing an AI system's qualia, so making AI systems that feel good, assuming that such qualia exists. So not arguing that they do, just assuming that they do. And typically as part of a broader objective that includes performance. So we're not just trying to make happy agents, we're trying to solve problems, but while also considering the agent's experiences. Yeah?
Just a clarifying question. So we assume that something like my feeling of my experience of the redness of red exists, but we're not assuming anything about it being interesting. Like it doesn't exist a thing like the redness of red.
Right.
My own experience.
Yeah, and specifically we're assuming that AI systems. Yeah. Okay, this is to remind me to tell you this work is an exploration. This is not a paper where we drive to some end message and that's the conclusion and we're going there. We're going to explore this space and we're going to go down a path, hit a wall, go back, go down a different path, hit a wall, and go back. And more specifically, we're going to formalize qualia optimization, put math to the specification of this problem. We're going to make guesses about what might feel good for an agent, but those guesses will be inspired by theories of mind like functionalism and computationalism. And when we do this, we'll encounter concrete mathematical problems with the formalization that we came up with, and that'll cause us to back up and change our formalization again, but it won't fix all of the problems. And so in the end, we're going to conclude without any satisfying formalization or a guess regarding what might feel good for an agent, but with some directions and algorithmic changes that seem more promising than others. Okay, so let's dive in. Starting with formalizing qualia optimization, let's put math to this. There's no need to reinvent the wheel. We have mathematical models of agents interacting with environments in MDPs and POMDPs, so let's use them. But they're not quite everything we want yet.
I just have a question about your second assumption. So you say we want to improve the AI agents quality, right?
Yep.
And just to get back to your first slide, you said that you were training the dog. We're gonna, if we have the choice between training the dog, we'll train the treasure, the treasure. But here it means something else. It means that the learning process has to improve quality, which is even different than what we're going for the dog essentially.
Right.
We want the dog to learn to catch the ball. But here we want AI to have great quality.
And to catch the ball.
And okay, so
it's both. Okay. Yeah, it's let me go to here. We're trying to improve agent's qualia, how it feels, as part of a broader objective that includes performance. So we want to still solve tasks that we care about. Okay, so MVPs, let's use them. But they have a couple problems, two problems that we need to fix. They're really simple. The first one is MVPs and POMDPs specifically only model the environment. They're not a model of an agent. And qualia is a property of the agent. So the fix is simple. Let's also model the agent. Let's also model the state of the agent over time. Okay, then we run into the second issue, which is not all of the agents and environments that we might want to consider include rewards. Maybe we care about supervised learning, sequences of predictions where there is no reward, or an RL formulation that doesn't include rewards. So let's make rewards optional. And when we do that, we end up with a system, which I'm calling an agent environment process, because it's a process of an agent interacting with an environment, where the environment has some state, just like before. The agent makes some perception of that state. We'll talk more about what that is relative to POMDPs in a moment. The agent then, based on that perception, chooses an action based on its current memory MT, and it updates its memory, chooses an action that changes the state of the environment, and this process loops. So it's an MDP or a POMDP with agent state added in. Okay, I just call this agent state, but I wrote memory. The reason is I didn't want to conflate the words state for agent and state for environment. So we're just using different words to correspond to the two, but you can think of this more as the state of the agent. Or alternatively, whatever is in RAM for the object that represents your agent, a dump of that is the memory MT. Okay, how does this relate to MDPs and POMDPs? Well, we retrieve MDPs if we define our perception to be a concatenation of the current state and the reward RT, and we retrieve POMDPs if we make that perception an observation and a reward. Okay, I'm about to introduce an assumption that I think many people might disagree with, but it's not really important. It comes up as one nuance right in the end. So if you don't like this assumption, don't worry about it for the vast majority of the talk. And that is that perceptions, PT, are part of the state ST. So you can write PT as a function of ST. The perception is included in the state. And similarly, the action is included in the memory. So the random things here are the state ST and the memory MT. Go ahead.
Partially included in the environment or fully included?
Sorry, I couldn't hear over the air conditioning.
Is it partially included in the environment or fully included?
Fully included. I can write PT as a function of ST.
So what about the subjectiveness of the perception?
I'm not sure I understand the question, what you mean by the subjectiveness.
So like the agent can have the environment can offer some perception, but the agent can subjectively have different perception of those perceptions.
I see. This word perception here has baggage attached to it, and I've used it in a way that baggage has caused confusion. So I mean, I'm calling this perception, but think of it as whatever aspects of the state are going to change the agent at future time steps. I don't mean how it feels as the agent to perceive this, right? Like I might see red different from someone else. And so if there's some light coming this way, we might have different perceptions of that light. And this is just encoding the light that's hitting your eye. Great question. Okay, so we now have our math model of the agent interacting with the environment, but what are the knobs that we can tune? What can we change in our efforts to make this agent have better experiences? Well, we want to be able to do things like redefine the rewards that we give to the agent. That we should be allowed to do. We want to be able to change the agent's perception. So hide part of the state, or maybe add something to the state or the observation that the agent gets. But we don't want to entirely disconnect the agent from the environment that it's working with. It should still be interacting with the environment that we're interested in. Okay, in an attempt to do this, we're going to introduce what I call the agent environment interface. So on the left, we have our base environment. That's just our environment from before. Now we're calling the state XT. And on the right, we have our agent with its state, its memory MT. And instead of them interacting directly, we're going to put something in between. This is something we create, and this is the knob we get to tune in order to try to improve the agent's experiences. And what it does is it intercepts the perceptions coming from the environment. It can change them and then pass them to the agent. For example, changing the rewards, right? Similarly, it can take the actions that come from the agent, change them, and pass them to the environment. We won't reference the fact that the AEI has state, but for generality, we do allow it to have some state. And notice this is still just an agent environment process from the previous slide. We have one big environment here that our agent's interacting with. It's just an environment that we can decompose into two pieces, a base environment and this mechanism, the AEI, that we can change in our attempts to make the agent have a better time while solving this problem. Yes?
And this makes me think, because you have like this diagram with like the -1s and then the +10 reward that's been like popping up. Like, I guess this, I feel like at first I was like, oh, okay, negative rewards is like something that would be negative qualia. But then I think like it's always relative, right? It's relative to like, the best positive reward you get. Like, so even if you do have this AEI, like how does this like, change anything in a way? Like, isn't there like
Beautiful.
like
You were the target for this talk. That is exactly where we are going, but I just need to build up.
okay,
answering
yeah,
that
sure.
question. Yes, this is perfect. This is great. It shows that I'm guiding you to the directions I want. Yes?
Part of the first section is also pursuing this, that there is some kind of like, version of Qualia, but we like still, this circuit, but layers to be responsible.
Right, yes. So we're assuming that the agent experiences things, it has qualia, but we're not making an assumption about what causes that. We're not assuming that it's due to emergent theories of mind. We're not assuming that it's due to a specific layer in a network. Everything we talk about should work for someone who thinks that, I'm blanking on the word, connectionist theories of mind are right, and a dualist should also accept it as well. Yeah.
So with that, then, these can also be like humans.
Absolutely. In the paper, I try to be clear when talking about AI agents versus just agents. An agent, this applies to us too.
What actually separates the interface to be part of the environment versus private?
This is great. There's a whole slide on this later. This is going to be a problem. Yes. Yes. I can repeat the question. Yeah. This question was, let me rephrase it in a different way, which is, why is the AEI part of the environment and not part of the agent? And the answer is, we will come exactly to that. Okay. We have our model of how the agent and the environment interact. Now we need to talk about what is our goal here? We said maximize performance, maximize the agent's experience. So let's start with the easy one, performance. If I change the environment, which I'm abbreviating to ENV, the AEI, this mechanism, or the algorithm, which is the algorithm implemented by the agent, changing any of these will change the dynamics of the whole system and could change the resulting performance on the base environment. So we can write performance as some function P of the algorithm AEI in the environment. I didn't want to reuse this symbol P because we use it constantly in math, hence the use of fractor, just to differentiate the font from the P of like a transition function. Okay, so performance is some real valued function of these three components. Like in reinforcement learning, it's the expected discounted sum of rewards, the expected discounted return. For simplicity, we're going to forget the environment. Assume there's some fixed implicit environment that our agent is interacting with. And so we can drop the environment term and just get performance of some algorithm in AEI. And none of these are actual meaningful assumptions yet. The meaningful assumption comes next, which is that performance can be expressed as a function of xt, a bar t, and pt. What is this saying? This is saying that performance is a property of the base environment. It doesn't depend on the agent other than through how the agent's actions influence the actions that go to the actual environment. What happens in MT is irrelevant if we end up getting the same actions going to the environment. So performance is a function of these three random variables, P, A, and X, that are coming from the base environment. But if I did this for RL, this would be like saying performance can be expressed as a function of RT. That's not true. It depends on all of the rewards. So I need to say performance, it's a function of these for all times T. And also that would just give me the sum of rewards. In RL, it's the expected sum of rewards. And you could have the median sum of rewards. So it's some function of the distribution of these random variables. So we need to amend this to, it's a function of the joint distribution of these random variables for all times T. And then we get expected discounted return, for example. Okay, now let's move to the harder one, which is qualia. So just as before, changing any of these three terms can change everything in the system. And so qualia could depend on all three. We're going to define Q to take all three and return a real value, and it's characterizing the quality of the agent's qualia, how good the agent's experiences are in this setting. And I will come back to the fact that this is a real value in a moment. Let's just get through the rest of it. So we're also going to assume some fixed implicit environment and drop it. So we have qualia for some algorithm and AEI pair. And just as performance depends on the base environment, what the agent experiences depends on what's happening with the agent. It depends on the perceptions, memories, and actions of the agent. If those are unchanged, it doesn't matter if you change something elsewhere in the state of the environment. So we can write this as a function of P, M, and A, perceptions, memories, and actions. And just like before, for all times T and the distribution of them. Right? Okay, let's talk about this being real valued. A common misconception is that I'm arguing that qualia are real valued. Qualia are not real valued. There's so many positive experiences. There's joy, there's satisfaction, there's the taste of sugar. All of these are positive qualia, and they're not just one real number capturing the full experience that we have. That's not what this is saying. This is saying that qualia quality can be measured with a real value. And if this is something that you're getting stuck on, imagine this example. If I wanted to measure the quality of our qualia, we could all rate on a scale of 1 to 10 how happy we are right now, how good we feel. We could take the average of that. That is a real valued measure of the quality of all of our qualia. It's not perfect. And then we can try to search for better functions Q, better measures of the quality of our qualia that avoid self-reporting, for example. But it should be clear that we can have real valued measures of the quality of agent quality, assuming that they experience quality at all. Okay. So we've defined almost everything. We just need to put it all together. So what is our goal? Our goal is to find the algorithm in the AEI, so we can change the rewards, we can change the RL algorithm that we use, that maximize both the performance objective and the quality of the agent's experiences. This is our problem formulation. This is a multi-objective problem, and we could phrase it as a weighted combination of the two objectives or maximize one subject to a constraint on the other. There are many other ways you can formulate this. We're not going to focus on one of these. We're going to look at this at a more general level of how can we increase Q with no change to P, is essentially what we're going to look at. How do I make the agent happier without changing performance? And we'll be able to find plenty to talk about even just in that setting. Okay, my hope is that at this point, this setup is actually fairly clear and solidified in your heads, other than the one glaring question, yeah, but how do you define Q? Was there a hand over there? No, I was imagining it. Okay, how do we define Q? This is the crux of the problem. So in general, for quality optimization, you can make many assumptions here. We're going to start with one, which is appealing to functionalist and computational theories of mind with the following assumption. If specific algorithmic processes and agents functionally resemble biological processes underlying human experiences, it's a mouthful, what is it saying? If there's something within an AI system that resembles something in us, but the resemble isn't they're made of the same material. The resemble isn't they're the same color, they start with the same letter. The resemble is they play the same role within the system. There's something that plays the role of pain in the AI system, it plays the role of pain in us. There's something that plays the role of rewards in the system, rewards in us. Then these corresponding processes yield similar experiences in both humans and AI agents. So let's say TD error plays the role of signaling a reward prediction error in an AI system. And in humans, dopamine plays the error of signaling a reward prediction error. Well, then maybe dopamine for us is what it feels like for an agent to get a TD error. Right? So that's assumption 3. Where we're going from here is assumptions 4, 5, and 6 are refinements of this to focus on specific things that we think might feel good to an agent based on them mirroring something in humans. Okay, so the first one is the most obvious, which is what we had started talking about. So assumption 4 says that quality of an agent's qualia can be measured in terms of the amount of reward it receives. Rewards feel good for us, maybe rewards feel good for agents. Okay. I have at least one colleague at UMass who read this paper, hit this assumption, and just tapped out and said, nope, I'm done. I do not believe this assumption, it's wrong. As was hinted at by someone in the audience, this doesn't make sense that rewards would feel good. I agree with you. What I thought was going to happen when I entered this project is this would be our straw man that we figure out how to argue against. We're basically sharpening our tools on this assumption of how do we analyze these, how do we talk about them. Then we get to assumption 5, which is the one that I thought is actually realistic and reasonable and the one that we'd end up using. We're going to end up sharpening our tools so well that we will quickly move past assumption 5 until we get to assumption 6. So if you're against this assumption, I'm with you, but I want to figure out how to convey what's wrong with it. And it was exactly what was described. Basically 20 minutes of that comment is what we're headed for. So let's ground this setting just a little bit more and say, what if our performance objectives, is just one example, is the expected discounted sum of rewards? Does my laser work? It does, okay. So what was I saying? I gave away where this is going. I didn't want to do that. Pretend you didn't see that slide that was coming after this. So we have the performance objective is the expected, this is the sum over episodes I, the sum over time steps within that episode of, I'll talk about gamma in a second. These rewards are bar, which are the rewards coming from the base environment. So this is the performance objective. what is this gamma to the p, gamma sub p? This is the reward discount factor that you'll get in typical RL formulations, but we have one that's for the performance objective, and our Qualia objective is the exact same thing, expected sum over episodes, sum over time, but perhaps with a different reward discount parameter, gamma q, and that reward RT is the reward that's going to the agent. So this is an example of how we might define P and Q in the reward Qualia setting. Okay, if rewards feel good and bigger rewards are better, what should we do to make our agents happier? Give them more rewards, right? So let's use reward bonuses. And the idea is really simple. Let's increase the rewards we give to the agent by adding some constant, reward plus C, to the reward that goes to the agent. Right? Okay, this will result in agents that have better experiences, better qualia in the reward qualia setting. Okay, but we aren't just maximizing the agent's experiences, we also need to think about what this does to performance. The RL people out there are probably going through a train of thought, which is, okay, negative rewards say get to the goal as fast as possible to stop the suffering. If I add a constant, they could become positive, which could change behavior because now I'm getting rewards and I want to avoid reaching a goal because that would stop me from getting more rewards. So adding a constant could change the optimal policy. But then you might think, wait a minute, if I actually add a constant to every reward, even in the terminal absorbing state, I'm just adding C over 1 minus gamma to all of my returns. If I shift all my returns by a constant, I'm not reordering my policies. Optimality is preserved in a sense. Yes, but that's not what we actually care about. We're focusing on one specific agent and how well it does, not the theoretical ordering of optimal policies, right? So for our agent, the reality is that changing the scale of rewards can change the hyperparameters that are effective for your RL algorithm. If you tune it to work with rewards on the scale 0, 1, and then you apply it with rewards on the scale 1 trillion to 1 trillion and 1, it's going to diverge. Your step size will be too big. So inflating rewards by C could decrease the performance objective. We need to fix this. Okay, well, I could try to adjust the hyperparameters. So I guess what I'm getting at is we're not going to fix this in the AEI. We'll fix this in the algorithm by making it robust to these changes in a sense. We'll figure out how we can change our step size and all the hyperparameters for our algorithm so that it performs just as well. Okay, that's an annoying thing to have to think through for every algorithm. How do I do this fix? There's a much simpler fix, which is change your algorithm so that it subtracts the constant from the reward, right? Okay, so what does the AEI do? It adds a constant to the reward. What does the algorithm do? It changes any reference to the reward to be the reward minus a constant C. If you have your TD error in a typical RL algorithm, you have the reward minus a constant C instead. Here's my new RL algorithm, and obviously performance is preserved. Because what did I do? In a register, I have my reward, I added a constant, I subtracted the constant, and I carried on with what I was going to do. Otherwise, nothing has changed, right? Yep.
Are you assuming that that specific constant is visible as a separate table from the reward? Because otherwise, you have to track it for a long time and then assume, like, if I give you a reward of +10, would you know that it's actually a reward of +2 and an additional constant of 8? Or like, is that?
No, it's all embedded into one reward. The agent just gets RT.
Is there a risk of not preserving the optimal policy because you would shift the reward by a non or like a different amount because you didn't track it long enough to then?
No, so just fix C10, right? I'm going to take this agent and just add 10 to its rewards all the time. And then someone else comes along and says, I have an RL algorithm that just subtracts 10 from the reward the moment it gets it and then carries on. We need to make sure we're aligned in those two. But if
he doesn't know you added 10, right? He just assumes.
Yeah. And his algorithm won't be effective for other problems.
Okay.
But in this exact pairing, we have a system where qualia has gone up and performance is completely unchanged.
So you're saying quality will change this?
Yes, because we changed the reward going to the agent.
Yeah, but that constant has no causal effect on anything specific data.
You guys are great. Okay, I'm going to keep going for a moment. Let's hold a bunch of these questions because I think we're going where you are, which is, this is silly, right? This is absurd. You added a constant, you subtract the constant, it does nothing. And so what I want to do now is formalize our complaints. I want to take exactly these complaints and figure out how can we precisely say exactly what all of you are thinking, which is great that all of you have gone down the same path. So how do we make our concerns about this rigorous? This is one way of saying what I think a lot of you have been pointing out. So let's look at this machine. Somewhere in it, it has a register that's storing a sequence of bits that we're calling the reward at time t. And there are many ways that we could encode, that we could view this sequence of bits as being a reward. It could be unsigned binary, it's 164. If it's signed, the leading one says it's negative 36. Maybe instead of reading left to right, most significant bit first, we could do least significant bit first and read it right to left, and we get 37. All of these are valid binary encodings. They're just representational choices. Okay, but proponents of AI consciousness typically think that what matters for consciousness is what is being computed, not the physical representation. We don't care if it's being computed on a brain or a computer chip, as long as they're computing the same thing, right? We also don't care if it's being computed using most significant bit first or least significant bit first, as long as they're computing the same thing, right? So what this means is that the representation that we choose shouldn't impact the value of the Qualia objective function, what the system is feeling, as long as it's computing the same thing. So if we look at the same physical system, and then we choose to use different representations of binary to numbers, that shouldn't change it. It's the same system. So this isn't the case in the reward Qualia setting. In the reward Qualia setting, how we choose to map these binary sequences to real numbers changes the rewards, and it changes the value of our Qualia objective function. And that's a problem. That problem with the Qualia objective function manifests in our solution of reward bonuses in that we can implement them with just a change of representation. I think this is what some people were hinting at. You can implement reward bonuses by not touching your physical system, but just saying, I'm going to interpret these numbers as being that value plus a constant c. I'm going to use a different binary coding where I just add a constant to the value I store. And the paper gives a little more detail on this, saying, what if I set out to actually implement a constant reward bonus? And I am going to have a different binary representation for rewards. I'll make a new instruction set architecture, a new assembly language that deals with these different binary representations. I will make new hardware to implement these operators with the two different binary representations. And then I will implement my system with reward bonuses. And what you get out is exactly the same system you started with without reward bonuses. So you can view that system as having or not having reward bonuses. We have one physical system. We can model it as, say, the PPO algorithm solving the hide and seek problem, or the same thing, but with reward bonuses. And each are equally valid models of the same system, and they result in different values of the Qualia objective, which is a problem. It's not feeling different things. It's one system. Yes?
There is a question online. What is MSB versus MSB?
Most significant bit versus least significant bit. Do you read the binary left to right or right to left? Yep.
I would argue that we have this problem with humans too. If you see how the self-esteem movement has evolved over the years, like in the old days, only figures were just yelled. Then there was some sickness, and everyone yells, then they were praised. But now that there has been this guideline of always giving praise, praise has lost its value. And now actually, like if you hear a lot of praise, you think you're hopeless. But if you hear a criticism, then then the person actually believes it.
There's pointing out, for the people who couldn't hear, pointing out that this mirrors what we're seeing in society with shifts in the interpretation of signals. And it's not the signal itself. It's this is really the core of this. It's not the signal that matters. It's how that signal causes an influence downstream. The same signal, if I change how do I say this clearly? That signal could change, but if I interpret it the same way and has the same impact on the system, there's no change, right? But if I keep the same signal but change how it impacts the system, that is then a meaningful change. Yes?
I think there's also argument that it's not the signal itself, it's the delta with respect to the baseline that matters. Like, for example, in dopamine system, you have two people that have different baseline will live the same experience very differently.
Right. This would argue, we'll get to dopamine in a second, that it's not the dopamine baseline, but the baseline of what a baseline amount of dopamine does to the rest of the system, does to the agent. This is an argument that we shouldn't try to measure the magnitude of a signal, because we can just inflate those arbitrarily. But the impact that signal has on the system is a different story, which is where we're headed. Okay, so we talked about this. Going back, so what do we want? We want this Qualia objective function Q to be invariant to these representational choices. How I choose to interpret binary sequences shouldn't change the value of Q. Okay, this isn't just about rewards, I want to point out. we can generalize this a little bit and say we have our AEI. Anytime when this AEI is performing an invertible transformation, we can put a mechanism in the agent that just inverts the transformation so that we retrieve the original perception. Anytime that we do this, if it changes the value of the Qualia objective, that's a problem, because this process isn't actually computing anything. It's just a change of representation. They're invertible transformations, like add a reward, subtract a reward. But it could also be an invertible transformation along the actions. I want to say not all cases are invertible though, right? So if I hide part of the state from the agent, there's no way the agent can invert that transformation, right? So we can have AEIs that are not invertible. This is just saying for the cases where it is invertible, we want an agent that just inverts it and carries on to not have a difference in the value of the Qualia objective function. So invertible transformations can be implemented with just a change of representation, but not actually changing the physical system. So the system's not changing, we should get the same value with the Qualia objective. Let's make this a little more formal. To do that, I want to review isomorphic random variables. If x is a random variable and y is another random variable that's equal to f of x for some invertible function f, then we say that f is an isomorphism and x and y are isomorphic. There's this invertible mapping back and forth between the values of x and the value of y. They're the same random variable, just with different values, right? Like I have a die roll that's 1 to 6 and another that's Monday, Tuesday, Wednesday, Thursday, etc. But they have the same distributions. They're the same thing, just with different values. Okay. Remember that our Qualia objective is a function of these variables, p, m, and a. And so let's consider two different mathematical models. One is alg, AEI, and environment, and the other is the same with tick marks, primes. And they have perceptions, memories, and actions, and p prime, m prime, a primes. They have different perceptions, memories, and actions. You could think of this as maybe one of these uses most significant bit first, the other least significant bit first, but these are just two different systems that we have math models of. Now let's consider the case where these are isomorphic. So if these two sequences, p, m, and a, of random variables are isomorphic, there's a one-to-one mapping back and forth between them, then they're modeling the same computational system. Might have different representations, but they're the same computation. And so what we want is, in this case, our Qualia objective function should give the same value for these two systems. We're going to call that representation robustness. So representation robust Qualia objective is one that defines Q to be the same for isomorphic systems. Okay, this slide says the exact same thing, just in different ways, in case it's more clear to someone else. This is exactly what we said before. If these variables are isomorphic, I guess I do have my laser. If they're isomorphic, if that and this are isomorphic, then the value of the Qualia objective is the same. Okay, recall that Q is a function of the joint distributions of P, M, and A. So another way of writing this is that Qualia is a function of P, M, and A, and law just means the distribution of. So we can write Q as a function of the distribution of P, M, and A. And from this perspective, representation robustness means that the Qualia objective should be invariant to invertible transformations of P, M, and A. If you perform invertible transformations to them, this function shouldn't change. Okay, what was the problem? I'll do this one, then take the question. I will sometimes say representation exploitable. That just means not representation robust. There's a question?
There's a question online. Well, you could have mapping from R1 to R2, so it is not per se just different values. I think it's okay.
For the sake of time, I think I'll take that one at the end. Yep. Okay. So let's go back to the reward Qualia setting. What was wrong? What was wrong is that the natural Qualia objectives that we think of for this setting are representation exploitable. We can inflate the rewards arbitrarily with just representational choices. Okay. We already talked about this, and I thought I deleted this line because we don't need to go over it. But you might think, but when I get a reward, it feels good. So you can't tell me that getting rewards doesn't feel good. And the point is, this is suggesting that the reward signal isn't feeling good. It's some downstream impact of getting that reward. It's the effect of the reward. Okay, let's move on from the reward Qualia setting. Let's think of something else that is in agents and us that we might be able to relate, and someone else also mentioned it. So our other hypothesis will be related to dopamine. Dopamine is a neurotransmitter, a neuromodulator. And the top is just to show this is coming from the Cleveland Clinic. They wrote, how does dopamine make someone feel happy? Dopamine is known as the feel-good hormone. It gives you a sense of pleasure. Dopamine feels good. Okay. There's separate work, wonderful paper. If you haven't seen this, please take a look at it, even if you forget everything I said today. A neural substrate of prediction and reward that shows that dopamine in animals corresponds to TD errors in reinforcement learning agents. They are encoding reward prediction errors exactly, they have the same meaning. And so in primates, dopamine has the functional role of signaling a reward prediction error. This was contested a bit. There were a lot of follow-ups saying, well, maybe it's only positive reward prediction errors. But the current trend seems to be, no, it's positive and negative, but maybe there are different dopamine-producing neurons encoding both of those. The very latest was arguing that normally in RL, we talk about the expected sum of rewards and the TD errors in terms of the expected sum of rewards. But it seems that for animals, dopamine encodes not just expected value, but other parameters of the distribution, like quantiles of the expected reward, not just the expected value. But the general idea that dopamine is a reward prediction error, it's like TD error at a high level, seems pretty established. So in many RL systems, TD error has this role. So we have these two things that are doing the same thing. Maybe they feel similar. Dopamine feels good. Dopamine corresponds to TD error. Maybe TD error feels good. So taking our assumption 3, that these two things resemble each other, we can now extend it to assumption 5. The quality of an RL agent's qualia can be measured in terms of the cumulative reward prediction error, the amount of dopamine you get, the amount of TD error that an agent gets. Okay, let's go through this one. Unfortunately, this has a lot of problems. The biggest being that dopamine doesn't feel good. There's a nice line of research now saying that dopamine corresponds to wanting, not liking. Stimulate the dopamine-producing neurons in your brain. It does not result in a pleasurable experience. And here are some references for this. And if you were at the last reinforcement learning conference, RLC, in Peter Diane's talk, he talked about things that people in the reinforcement learning community are missing from neuroscience research, and he referenced these results, that dopamine doesn't actually feel good. It's more of a wanting than a liking. Okay, so that undermines this whole setting. But still, let's carry on separate from that. Okay, TD error feels good. What do? Add a constant to the TD error and we get bigger TD error. So let's do the exact same trick we did for rewards. We'll add a constant to the TD error. To preserve performance, we then subtract that constant before we use it. So this is a typical, really basic actor-critic algorithm in RL. We add a constant to the to the TD errors. And anytime we use those TD errors, we subtract that exact same constant off. Nothing has changed. Our TD error is higher. Our agent is happier, right? It should be pretty clear at this point. That's representation exploitable, right? I can do all of this with just a change of representation, exactly like with the rodents, right? Okay, there was no hand. There's a common objection here, which is, but Phil, this is the TD error, not what you choose to define to be the symbol delta t. So in this equation, I said add a constant, and now the TD error is the shifted value. Someone might argue, no, you can't add a constant to it. The TD error is always this expression. And if you add a constant to it, that's changing how it's used. In the paper, we go into this and show that this is also representation exploitable if you define TD error this way. Okay, so now we keep hitting this issue that everything's representation exploitable. Is anything representation robust? So first, a negative result. Consider all qualia objective functions that take as input the observed states, memories, actions, perceptions, memories, actions, what's happening, the trajectory in RL, and then compute some statistic from that, some real valued statistic, like the discounted sum of rewards, the discounted sum of TD errors, the sum of state values. And after computing that statistic, we take some functional of this value. By that, I mean a function of its distribution, the expected value, the variance, the median, right? So compute a real valued statistic and then apply some functional. All such qualia objective functions Q are representation exploitable. They're not invariant to invertible transformations. One exception, unless this function G is already invariant to invertible transformations. That's not going to happen unless you kind of try to make it happen, and we'll talk about an example of this in just a moment. Okay, so nothing that we formulate this way is representation robust. We need something else. There is hope. The key is that we compute one real valued statistic. and then some function of that distribution. What if we compute multiple real valued statistics? Then the answer changes. There are Q that are functionals of multiple real value statistics that are invariant to invertible transformations. The best known being KL divergence or relative entropy. KL divergence is invariant to invertible transformations-ish. There's a condition here. It's only diffeomorphisms, so only differentiable transformations. So that means smooth mappings back and forth between the values of the two. It doesn't allow for these discrete jumps in your representation. Talking about something like a bit sequence, that's a problem because that's not continuous. But okay, there are others. There's mutual information. With no conditions, mutual information is invariant to invertible transformations. So if we can write Q in terms of mutual information, it would be representation robust. So we could have Q be something like the sum of the mutual information between perceptions and actions. But remember, our goal isn't just to come up with one that is representation robust. It should also mirror our phenomenology. It should mirror measuring what feels good for us and what doesn't feel good for us. And I'm not sure that this one does. And I brought up this picture to point out, there's another great paper by David Abel and collaborators talking about plasticity as the mirror of empowerment. It talks a lot about directed mutual information, which is also invariant to invertible transformations because you can write it in terms of mutual information. So you could go down the road of trying to think if there's a way to create a Q using this. Before we go to our next assumption, we're going to hit another wall, which is the AEI was just a bad idea for the reason that some folks are starting to point out. And we can characterize that with a simple argument. There's one solution that just always works, and that's the dual agent environment strategy, where we're interacting with some base environment. So we create a dual agent. We make this some agent that's really effective. Ignore agent experience and just use the best RL algorithm you have and have that solve the problem you care about. Then create some other environment, which is just all sunflower and rainbows and puppies. It's the happiest it can be for the agent, and have your agent interact with that. And your agent, this algorithm, doesn't need to worry about performance. It only cares about maximizing the quality objective. And when you write down these quality objectives, trying to come up with degenerate agents and environments that maximize it is relatively easy. So this will result in the best performance we can get and the best qualia we can get. But it's doing it by ignoring the problem we set out to achieve, right? We wanted an agent that solves the problem and has good experiences. And we said, okay, here's how you do it. Put that agent aside, have a different one solve it. You don't care about its experiences. And then have the agent you care about solve some really simple problem. That's not addressing the issue. And the core reason for this is we defined this AEI to be something that we didn't care about its experiences, right? We put the AEI inside the environment, not inside of the agent. And so if we do want to care about the experiences here, we would need to move the AEI inside of the agent. The moment we do that, we're just back to our original AEP, agent environment formulation, with no AEI. And so that's the route we're going to go. We're going to go back to just having an agent interacting with an environment. There's no AEI anymore. All that we can change is the algorithm. Okay, let's move to assumption 6. Assumption 6 says that the quality of the RL agent's qualia can be measured in terms of the reinforcement of behavior. So this means I recently did something. I can now learn and say, okay, I want to make that more likely. I want to do that more often in the future because that was good. We're saying that feels good to the agent. Or if it does something and that turns out poorly, it says, I didn't like that. That didn't turn out well. Do this less, right? That's inhibition. Inhibition would feel bad. So reinforcing behavior feels good. Inhibiting behavior feels bad, is what this assumption is saying. Okay, let's see what happens if we use this one. One way we could write this using classical RL notation is as the expected sum over episode, sum over time steps of the likelihood ratios. So this term pi says how likely is it that the agent takes action AT in state ST? And this is the agent's policy parameters. It's memory after the learning update, and this is before. So when this is bigger than 1, it means that the agent is now more likely to choose the action it took. And when it's less than 1, it means that the agent was more likely to choose this action previously, before the update. So bigger than 1 is reinforcement, less than 1 is inhibition. Yeah?
Should this be somehow also weighted by the sign of the reward? You can force me to do something I'll do it more. Doesn't mean that I'm more happy to do it, right?
Yeah, there's a question, yes. There's a question of how well this aligns with what we experience. And I'm going to put this off for now to get the material. Yeah, this will be a longer discussion. So I think there's a very valid criticism, which is, does reinforcement of behavior actually correspond with what feels good or bad? Roughly the direction I would go is, I don't know. But I want to think of reinforcement of behavior at a lower level than just like my macro behavior, but at the level of like the raw outputs of the agent. And perhaps that's including like what you're thinking and your thoughts and everything that's being updated. Perhaps when that's happening, yes, your macro behavior is some sort of reinforcement. I'm going to do this thing more, but there's a lot of inhibition going on in other aspects, perhaps. Okay, but wait a minute. This is a real valued statistic. This is a functional of a real valued statistic. Shouldn't be representation robust. This is that edge case, unless our statistic is already invariant to invertible transformations, and likelihood ratios are. So this is already invariant to invertible transformations, and this Qualia objective function is representation robust. Okay. I'm going to skip this for the sake of time, but I'm going to summarize it. So I cheated here. This is classical RL notation, not our notation for modeling the agent in the environment. And this works, but there's a problem when you try to do this in our formulation. And essentially the problem is the agent's memory. This is saying, what if I were to go back to this situation and redo it and say, okay, go back in time. If I were back in that situation, would I now be more or less likely to do something? To go back to that same situation, we need to roll back some parts of the agent. If the agent changed its belief state as a result of what it observed, so it observes something and thinks, oh, the state of the world is completely different from what I thought it was. To go back to that same state, I need to undo those contextual updates within the agent, but I don't want to undo the learning part, the part of its update that is part of the policy update. And there's no way to tease these two apart for a general agent. How can I put a divide in and say, okay, that part of what the agent did is learning and that part is just context, right? You can't, in general, as far as I know, do this. Here we're cheating by saying we have some division into these are the policy parameters and there's no notion of belief state or current context. And a couple other issues come up, which are outlined here, but I'll skip over it for now. I can't move this to the notation that we have for AEPs. But we have a path forward by considering policy gradient algorithms where there is a clear division into a policy update phase and an action selection phase. And so in that case, we can talk about our classic notation where we have choosing some action given the state, and these are our policy parameters. And that lets us use our objective from before. But I want to admit, this is a path forward by just ignoring the problem. By saying there is a clear division, even in these cases, it's not clear that that is the right division. So one area of future work would be how exactly do you define reinforcement in this setting? Okay, so this raises the question. We have a Qualia objective. Can we bias agents towards learning by reinforcement rather than learning from inhibition? The answer is yes. We can just only allow policy changes that increase the chance, the likelihood of whatever actions were recently chosen. Right? So this is possible. But can we still learn optimal behavior this way? If I've learned a bad habit, I need to unlearn it. Can I unlearn my bad habit and get to an optimal policy when all I'm allowed to do is reinforce my behavior? The answer is still yes. And we can achieve this by changing the magnitude that we reinforce. Reinforce the things we want more than things that we don't want, and we'll still end up reinforcing what we want and inhibiting what we don't want. Okay, but does adding a reinforcement bias significantly hurt performance? Well, it depends. And to see why it depends, let's look at policy gradient algorithms that have baselines. This is various forms of the policy gradient expressions. The baseline is this constant that you're subtracting off. In the Sutton policy gradient paper, they subtracted from Q. In reinforced, you have a baseline that you subtract from the return. These baselines. In the paper, we argue that reinforcement is controlled by that baseline. If you scale that up or down, you're scaling how much the agent learns from reinforcement or inhibition. Okay, so what does this do to performance? Well, we set those baselines to minimize the variance of our policy gradient updates. It's the optimal baseline minimizes variance. If I change that baseline to encourage reinforcement, I'm going to have higher variance in my policy gradient update. Okay, but when is that really bad and when is that not bad? It's hard to think about when you just think in terms of variance. There's a beautiful paper by Wesley Chung, Valentin Thomas, Marlos Machado, and Nicholas LaRue that argues for a different perspective on baselines in reinforcement learning. And specifically, they argue that even more than just the variance, we should think of baselines as in terms of how they change the learning behavior of an agent. And they focus on committal behavior or non-committal behavior. So committal behavior, and they argue that baselines are scaling this. So committal behavior means the agent does something, it turns out better than expected, and it says, I'm going to massively commit to this. I like this song, I'm only listening to this song over and over again. A non-committal agent would be one, or like a less committal agent would do something, it turns out better than expected, and it slightly increases the chance that it does that in the future. A non-committal agent would be one that does something, it turns out better, and it still says, I'm not sure, I'm gonna do that a little less. But when something turns out horribly, it says, I'm never doing that again. That's committal versus non-committal. And baselines are scaling that behavior of the agent, and that might have a bigger impact on performance than the variance reduction properties, is the argument of their paper. And reinforcement corresponds to committal behavior. Inhibition corresponds to non-committal behavior. So a hypothesis that comes from this is that reinforcement bias might have little impact on performance for non-adversarial environments, but significant impact on performance for adversarial environments. By non-adversarial, I mean typical environments, like pick an arbitrary grid world, right? Yeah, sometimes the agent will favor actions that aren't the best one initially, and it'll have to learn not to take them. But that's different from environments like chain domains, where if the agent starts here and if it chooses action A2 twice in a row, it gets a reward of 10. But if it ever chooses action A1 before it gets there, it gets a smaller reward and it terminates, right? In this case, the random policy is more likely to accidentally choose A1 too soon. And it gets a small reward and says, hey, I should do that more, right? Now it's even more likely to accidentally choose A1 and get that reward and say, hey, I should do this more. And that overcommittal agent will commit to choosing A1 and have to eventually unlearn it. The baselines are, you can show that this is still the correct gradient estimate and expectation, so everything will work eventually, but this can slow down learning. And that's exactly what we saw. So these are typical learning curves with episodes across the horizontal axis, performance return across the vertical. The black curves are no reinforcement bias, so it's doing both reinforcement and inhibition. The red is a bias towards reinforcement, but you're still getting both updates. And the blue is essentially only reinforcement, learning just from reinforcement. And you see essentially no difference for the grid world, but you can see that there is a significant hit in performance for those environments where the agent is driven to favor suboptimal actions initially. Yes?
So we feel negatively valence qualia, that suggests that for optimal performance, you can't just, only have reinforcement and no inhibition and still get good performance. Your team could sum that out.
Yeah. So to repeat the question, if we assume that we're optimal agents, like evolution did a great job evolving us, we have negative experiences. So does this say that this is a case where you need negative experiences? It could be. It could mean that we're in a world that has a little bit of this. Also, evolution had no force pushing it towards an incentive to make us feel good. And so it could be the case that there's a very slight hit to performance to only learn from reinforcement. Okay, so the conclusions from these, it's weak. Like these were two really simple toy problems. But we can tell from this that reinforcement baselines don't always have a big impact on performance. We saw that with the grid world, where we learned almost entirely from reinforcement and there was no difference. But that they can have an impact on performance when this overcommittal behavior causes the agent to choose the wrong actions and commit to them too quickly. Okay, I do want to point out that I worked with an honors undergraduate student, Derek Lacey, who's now a master's student, who, for his honors thesis, which hopefully will be out soon, he proposed 3 different methods for adding a reinforcement bias into PPO. And each of these comes with a parameter that lets you tune how much it favors reinforcement. And an interesting result was that for Majoku and ALE Atari experiments, they resulted in different trade-offs between performance and reinforcement. So different ways of adding that bias resulted in more reinforcement with less penalty in terms of performance. And also, he was doing this around the same time that I was writing the Qualia Optimization paper. And so ideas went both ways, surely. Okay, so to wrap up, I hope you come away from this thinking, yes, we can put math to the problem with Qualia Optimization. The agent environment interface is a natural thing to include, but we shouldn't. It allows for this degenerate solution. Many natural qualia objective functions that we might think of when we first think of this problem are representation exploitable, like the expected sum of rewards, the sum of TDRs, the sum of state values. That the reinforcement qualia settings result in naturally representation robust qualia objectives. So reinforcement might be a way forward, but there are issues with this. It's not clear how we should define reinforcement in the setting, and it may not align with human experiences of what's good and bad. And also that sometimes we can actually insert a bias towards reinforcement without a big change to performance. Some directions of future work, there are lots of general directions. My top 4, the first is, can we find a representation robust quality objective that aligns with our human experience? And a starting point would be, is there a general definition of reinforcement learning? Sorry, of reinforcement, not reinforcement learning. And can we automatically tune hyperparameters that scale a bias towards reinforcement so that they don't result in a significant hit to performance? If that's the case, there may be little reason not to include these because it doesn't hurt performance. I'd also love to remove this kind of arbitrary boundary between the agent and environment and instead consider the experience as the whole system. And this is actually the one I'm thinking about the most these days, which is what are the implications if this whole process is deterministic and there's no stochasticity in the system? And a wild one is to consider not treating time as a special dimension relative to others. All right, that's it. Thank you for your attention.
So does this framework, this psychology, that's that you froze an agent, they get a cat experience, pain, pleasure,
This is the best. These are all the questions that I wonder about. This one doesn't bake that assumption in because qualia is a function of the environment, the AEI, if we include it, and the agent as a whole across all of the time steps. So it could be that this value of qualia only appears when you consider multiple time steps. But I think this is mentioned at the end. An interesting question is trying to look at how different Q functions either do or do not require a change in time to cause any value of qualia. Like reinforcement bias, the reinforcement qualia setting, that one requires 2 time steps to talk about how things are changing over time. But TDR or reward don't. You can take a slice of time and talk about what the agent is experiencing at that slice of time.
Yeah, thanks for the great talk. Also, thanks for guiding us through all the hardships here. So if I'm not wrong, it seems that you just used in order to framework the fact that qualia needs to be invariant. Like you just adopted.
So it needs to be what?
Invariant. Like you just
Yes.
adopted that function is
Yes.
You never use the fact that qualia need to be need to satisfy the property that people who strongly hold in the belief of qualia believe into. Like the fact they're intrinsic, private, ineffable.
Mhm.
So it seems that you can make a stronger case here by saying that you talk about the quality of experience as opposed to quality of qualia, and this would extend your work like without changing anything, just changing the word to even people who don't believe in qualia, right?
I see. I think I see. I followed most of this until the difference between qualia and experience. You're saying that I could pitch this as improving experience, not necessarily improving quality.
Yeah, exactly. We never use the properties that people attribute to qualia, like the fact they're private, ineffable,
Right.
inaccessible.
What
We
I
just use functionality.
Where I thought this was going was to say we could add those assumptions in, and that could inform this even more. Yes, and I think that would be interesting. I don't follow when you jump to, but this wouldn't be an issue when we just think about experience, because I don't understand the difference between experience and qualia. So what would it mean? What is experience if not qualia?
I think this depends on who you ask. Like if you adopt like a Dennett or Frankish perspective, like you can have experience, you do have, again, like you don't claim that such experience comes from anywhere else than functional properties that you have. There's nothing private about that. There's nothing special about that.
Yes.
There's nothing universal about that.
So yes, I think I agree entirely. And it would be neat to look at how adding those properties into this change what properties of Q we would want in a formal math way. Something I like about this is that this still works for dualists. So for those who aren't familiar, dualism is when you think that there's a separate, think of like mind substance that is separate from the physical world that we live in. The assumption 3, I pitch it slightly poorly. I describe it as this should agree with functionalist or computationalist theories of mind. It's not just theories of mind, it's theories for the valence of qualia, the sign. So it's okay if you think that what causes something to have consciousness is based on dualist theories. And it's not just about what's being computed. This still applies if you think that the valence of those qualia, whether they feel good or bad, is scaled by computation. So this assumption is saying how something feels good or bad is determined by computation, not whether or not something feels. That we're just assuming. I think that hand is first, and then over here. Yep.
Thanks for the talk. For questions. So, one, yeah, I guess the first one I'll ask. This, back to what I asked before, was like this assumption that the agent just has a qualia. Other than like to properly test your hypotheses, should we actually just try and test this on humans first, or probably have like a stronger assumption that we have qualia versus?
Yeah, that goes exactly to this one of, can we find these cues that align with the human subjective experience? I mean, the test for this would be these different cues, when we apply them to us, are they accurately capturing what feels good and what doesn't feel good? And as people were doing, they were coming up with counterexamples to, well, for that reinforcement cue, here's one that maybe doesn't align, but then maybe we have to rethink how we're defining the action space in this case, and maybe it does. But exactly, that is the route that I think we should take. The one thing we can evaluate is our own experience of what we think feels good and bad. And we should use that to try to pick which cues seem reasonable or not reasonable. One of my fears going in is that there would be so many that are reasonable, how can we decide between them? And I've been a little surprised to find, instead of there being so many, I have none that are reasonable. Yeah.
And the other is kind of that last point as well. Or I guess your second last.
Okay, yeah.
Yeah, using the models kind of also assumes determinism a little bit because we probably learn their environment and all that. Where yeah, for humans as well, we don't know. We maybe don't.
Oh, interesting.
Sorry, could you just repeat the question?
Yeah, so I think the question was pointing out that when we're dealing with the AI systems, there is determinism, but with humans, there isn't necessarily.
There's some stuff has to be.
Yeah.
Like we are fully controlling. Very lucky.
Yeah. I guess, so there's deterministic versus stochastic, and then there's the amount of control we have over the system. So for the AI system, yeah, we have a lot more control than we do over how I would make an AEI to change your experience so that you're having a better time, right? I have less control over that. But I actually view it the other way of, in our AI systems, we can essentially have non-determinism, randomness all the time. And we use pseudo-random number generators, but you could get an actual random number generator and have real randomness in the system. Are we stochastic or are we deterministic? I don't know the answer to this. My understanding is we don't really know if the world is deterministic or stochastic at a fundamental level, but that at the level of neurons, it's essentially deterministic. And so if at the level of neurons, it's essentially deterministic, and then at the level of our behavior, it's essentially deterministic, something like the reinforcement qualia hypothesis doesn't make so much sense because the probability I choose an action is deterministic. So that's where I was getting with this one. Yeah.
Like last time. So another assumption as well that would kind of like have to be made with the assumption for having fault is that these models then have also developed a sense of self.
Why do you think that one is necessary? I'm not objecting that we might not want it.
Yeah,
but
I feel like when understanding the experience or quality of the phenomenal consciousness, it's like there is this subject within that like mind feeling. It's like what is doing line up.
Yeah.
Yeah, I see red this way, you see red that way.
I-
So, I actually checked it on.
Yeah.
It's like,
I think there are a lot of people who'd agree that that is baked into assumption one, is there's this kind of like self-model of some sort or self-awareness of some sort. But I didn't want to bake that into assumption one because I'm pretty sure there are many people who wouldn't agree with it. And it wasn't something that this work hinged on. Yeah. Okay. Yeah.
Thanks a lot for the talk. It's a very fascinating theory. about one-time qualia, and it's very helpful once we cross that bridge. There is a dilemma that we don't know when we cross. For example, ChatGPT trained it adversarially to say it's not conscious, it doesn't have the qualia.
Yep.
But well, it's unlikely that it does. But if it suddenly did, it would keep saying that because it would be painful for it to say it has quality, have it associated with that.
Yeah.
So how would you?
Yeah. Every response. So the question, to repeat it, was ChatGPT now doesn't experience qualia, but we train it to explicitly say that it doesn't experience qualia. And so what if in the future it does start experiencing qualia, but it's trained to keep reporting that it doesn't, so we don't know it does, and we don't know when we need to worry about it.
Exactly, because we've effectively forced it to lie to us about it if it does.
Yeah.
Because we've conditioned it to say that condition, we punished it every time that it did.
So I have dodged all of these questions in this work, in this talk, very deliberately, because these are really tough questions that I'm not equipped to answer. The thing that I struggle with is I don't know if any of you are conscious. I don't know if ChatGPT is conscious or not. And I am willing to look at you and say, well, I'm going to worry about how all of you feel, even though I don't know that you're conscious. And for an AI system, at some point, it seems like the general public is heading towards thinking maybe they are feeling something. So I think regardless of our own views of this, there will be more need for work that asks the question, well, what if we do want to worry about how they feel? And an interesting result would be if we could say, we can get essentially the same performance while optimizing metrics that might characterize how they feel. But it's extremely speculative, right? Like, we have no idea whether reinforcement actually corresponds to what feels good. And we have no idea whether that system feels. And so it would be quite a leap to say, so you must consider this when you design AI systems. That would be a massive,
Thank you for the talk. I thought it was interesting how your environment and agent transitions look so similar to each other. They both have states menus. Do like actions percepts. Here you want to also remove the agent and environment boundary. So I was wondering if your definition of agency is something that does Qualia optimization, or if the environment itself isn't doing kind of optimization.
Okay, so first, I agree there's a symmetry between the agent and the environment here. It's identical on both sides. The question was whether my definition of agency is that it's something that does Qualia optimization. I don't think I'd say that because not everything has to worry about Qualia optimization. It can still be an agent. But the bigger, higher level answer would be, I don't think I have an answer to what agency is. So that kind of undermines my ability to say like agency means that you perform Qualia optimization. Sorry to have a kind of non-answer to that.
No, it's fine.
Yeah, I think it was in the back and then here.
So like, something is not that, like, what is a reward of an agent? You define the quality as a function of some variable. But what is it exactly for an agent? Is it a change in its parameter? That's the only thing I can think of that an agent can experience, like some reward or like some quality. And if that's the case, have you thought or explored like it's like basically we have like this functional equivalence with the parameter that won't change the policy whatsoever. And have you thought about like these functional equivalent parameter having different qualia for the agent?
So I don't know what you're referencing with the functional equivalent parameter, but let's talk about the first part. Sorry, so the first part, remind me, what was the first part of this?
What is the reward of
Yes.
the agent?
Yeah, and you mentioned you were thinking of the reward of the agent as being the change to its weights, for example. I would consider the change to the weights as something else. That would be the change to the weight. And it would still be representation exploited. But I was thinking of the reward as if you're doing the Atari games with RL, it's the reward RT. It's the change in the score of the Atari game. And we compute this, and it's
that change to the agent. It doesn't like know what it is. It's just the only thing that the perception of the reward for the agent is like the change in its parameter.
I think we're in agreement. So I think what you're saying is that's a silly way to define quality. And I'm agreeing that we shouldn't define it to be RT for exactly what you're describing. The reward RT is just this signal, and you're arguing it essentially like the agent doesn't perceive that. And I guess this is essentially trying to argue the same thing, that that's not, if you take these computational physics of mind, that's not what the agent is experiencing. It's something else. It's something about how that reward influences something in the agent, like the weight change. And so we want to then say, okay, it's not a reward, it's the weight change. But the way I was trying to argue that was by saying, what is it that says it's not the reward? And I take the view representation exploitability is the issue. So it's just a change of representation. The change to the weights is also just a change of representation. And so the same argument could be made to say the agent doesn't experience the change to the weights either. And if we keep going down this, we need to find what does it mean to be a change to the agent that isn't just a change of representation. And that's how I ended up on the reinforcement hypothesis, which is taking exactly that. So the reward changes the weights. What is that doing? It's changing what the agent does. It's changing it to be more likely to do something in the future. It's looking at the external behavior of this agent system as opposed to just tapping a signal inside. Because whenever we tap a signal inside, we can just exploit that by representational changes. Does that make sense?
I have there's some nuance here. Like for example, you can change the parameter based on the agent, but the agent would still perform functionally equivalent under our specification of the problem, under our environment or whatsoever. For example, one simple example is multiply one weight by C and divide the next layer by one divided by C. You are changing something about the agent, but the agent is functionally equivalent. So, but I'm saying this change in the weight can result in change to the Qualia movement.
Right. Okay, let me repeat the question. So the issue you're pointing out is that we can have changes to weights that don't change the agent's behavior. It could be two things that cancel out in a neural net, or another classic one is softmax action selection. A softmax policy where all of the values are 0 is the same where all the values are 1. Right? It's still uniform random. So you can have these changes that are changes to the actual weights, but they're not changes to the behavior of the agent at this bigger level of action probabilities. So the argument is that is still a valid change. The counter argument would be those changes aren't changing what's being computed. So I could implement that same algorithm without that in it, and I would get the same exact system, the same thing being computed. And so it's just computation. If we're saying it doesn't matter if it's a brain or a CPU, if it's computing the same thing and it experiences the same thing, those should have the same experiences. But there is another angle to this where I'm struggling to fully wrap my head around this direction, but I think you might be able to make an argument along the lines of that change is a material substantive change. And what do I want to say about this? No, I agree with this gut feeling of, but there's a material substantive change. And I think where this would go is the line of arguing that it is not what is being computed that influences it. It's something about the material substance that does it.
But that changes.
Yeah, and so it could be that qualia is produced by some physical substance, right? Like dopamine causes consciousness, maybe, I don't know. And if that was the case, then a system without dopamine, without some physical property, wouldn't have it. And that would undermine all of this because this is taking that computational perspective. But I do want to say, I would love to try to study this without the computational assumption. It's just really hard to make headway because we don't know what the substance is that matters.
Another question, what is there a relationship between let's say existential, being aware of your existence and qualia? For example, acting towards an existential danger. If an agent acts towards an existential danger, then can we say something about this qualia? And if that's the case, we have seen these AI models acting.
This is a question for a philosopher. I don't know. I bury all of this within assumption 1, which is saying they do feel. And I guess this question is saying, do they have to have some existential awareness of themselves existing in order to satisfy assumption 1? I don't know. Did you still have a question?
Maybe the last question. questions.
Okay.
because- And then one question on land.
Okay,
For the-
yeah.
If given the opportunity to, without changing your performance or your experience of positive things, would you eliminate pain from your?
To repeat the question, if I could not change my own performance at anything, but I could eliminate pain, would I? That's interesting. It would depend, like, by eliminating pain, am I changing the valence of positive qualia?
Imagine your positive, your.
Stays entirely unchanged, then yeah, sure, I get rid of back pain. Great.
But your perception would change. Your perception.
Right, so I don't think this would happen, right? If I got rid of that negative pain, the positives probably wouldn't feel quite as positive. But this is very speculative, and I feel comfortable talking about like the math sides of these. When we get into these more, this one isn't really philosophical. Yes, this is philosophical. I'm less trained than, I'm not a philosopher. I'm a RL researcher.
I guess I'm pushing back to the optimization of qualia being the ziteron for taking qualia seriously. I know that you want qualia to be good, but you just want to be in a sense, like you need to, I don't know, there's a way of approaching and respecting qualia that doesn't require.
Can you say a little bit more? So,
in a way that you pursue include reward.
so you're saying that we can still think about and reason about and respect qualia as being there in agents
Without
and not worry about
worrying about goodness.
goodness of it. Yes, that I guess is assumption 2. So I've dodged a lot of these really challenging questions with assumption 1 and assumption 2. 1 being AI systems are conscious. What the preconditions are for that to happen, I'm not addressing. And this one is, assumption 2 said there's some need to worry about the experiences of the agent. And you're saying, well, that might not be there. We can also still reason about qualia of agents without worrying about trying to make them feel better. And that's also true and was dodged with assumption 2. But, oh yeah, I'll just leave it there. What was the online one?
Yeah, so first Glenn is saying great talk.
Thanks, Glenn.
And then, the question was, does this matter if the agent is only headlessly simulated as numbers, which means the computations can be done at very different locations in a distributed system? Or do we need some kind of integrated computational architecture, example, a local boundary computation?
Yeah, I love these questions. So we said all that matters is being computed. What if what's being computed is separated vastly across space or even time, but it's still being computed? This is saying it's just what's being computed that matters. But we have this natural sense that you would want these computations to happen locally in space, for example, is what I think this is asking. This work does not address those questions at all. And I think it's interesting and fascinating, but I don't have any deep insight into that question. This assumption is just saying, if it's being computed, that's what matters, not where is it being computed or how. Yeah. All right, this was great. Thanks, everyone.
Okay, thank you so much. After you can talk,
We have a lunch first.